get all 5 of you and you to come down? So how many is that? 1, 2, 3, 4, 5. You 2 I need. 6, 7, 8, 9, 10. Okay. Come over here, okay? Come over here. Everybody coming really close, right? You need to watch your little two seconds. You need to come around this side. You follow people. Alright, so we're going to show. I want you to tell me what's going on. Okay? Can you come help too? I have 10. What happened to my other person?
She stayed there. You were supposed to
more. How about you? You guys.
I can help. I was going to say. You need?
No, you're it. Perfect.
Yes! Hunter, you're up.
All right, 1. Remember your numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's really easy. Come here, guys. Pay attention. So, when we go through 10, my number is 1. Put this down. It's a 10. And count 10 more cards. 1, 2, 3, 4, 5, 6, 7, 10. Unfortunately, it's another 10. Okay? So I got to count 10 more. Get the idea of what I'm doing? So, did you get what I'm doing? Okay, so pick a number, don't tell me what it is. And we're going to go through and eventually I'm going to say, this is the next number. Okay? Do it first. So pick a number, don't tell me what it is. Okay? You ready? Slow. The next card is the next one you should be at. Am I correct? Or not? You didn't follow what I'm doing? Or you did? Did anybody else do it? Alright, so everybody just do it with your number. Remember your numbers? Okay, but can you do it like every time your number? So I got the number right, alright? And I want to show all your numbers are going off. Okay, so this time when you do it, I want you all to watch it. So like you're number 1, right? So I'm going to show you this. Right? So like, so you're currently 1, you should have 1 finger up, you should have 2 fingers up, right? So then as I flip, you're going to now change yours to 3, right? Because your 1 is gone and now you're at 3. You get it? Okay? And you should now be at 1 finger, right? Because I turned 1 card to 2, right? You're counting down, right? So you were, no, you count 1 down every time you flip a card. So you were at 10, now you're at 9, right? You're at 8, 7. This is what I want to make sure everybody got it, all right? Hold your hands up high so everybody else can see, right? And we keep going, all right? And when your number comes up, okay, so start over again. So what's number 3, right? So I have 2, 1, right? You get it? So you got to 8 fingers up. I actually want to do it because I want to see that, like if you notice, like you got 8 and she's got 8. Right? Okay, so you're number 8, right? So now you're 7. We're coming down until we get to your card. Now you're 6, right? Every time you put 1, flipping, right? So yes, you're at 10, good. You're at 10 now, right? Taking your card. So you're at 1, right? You guys keep track. That's my practice, right? You're at 1, right? Okay, so you're number 10, right? Excellent. You're 8. All right. Keep your fingers up for 1 so I'm trying to see. You guys.
I wasn't paying attention.
All right, but during the second one, you need to pay attention. So let's try to get once all the way through. These guys get it. You guys ready? And during the thing, you're going to have to look up there. So we're going to have you out here, like standing out here with your hands so you guys can see the cards, because I'll put the cards here and they'll show up there. All right, but everyone's got to look up. Ready? All the way through. What's that? I'll let you watch that. Are we ready? Okay. You. Excellent. You. Right? You went. Search on 3, 2, 1. So this was you were 3, now you're 2. Right? Are we out? Let's try all the way through. All the way through. Ready?
Yeah, like that dark thing goes from they're having all the different
Right? Right? Right?
so it's like a competition with all like high tech people who are like having to sort of like turning a knob or something. Yeah. I love that. So great. Yeah. That was awesome. I'll tell you about it. I think it's gonna happen this year.
With me?
I did like okay. I wish I had more time. Like we're gonna do story time and I did all these more things.
So you're going to be able to do this? Are you with me or not? So don't just do you not get it? You get it? You get it? You two guys get it? Are we going to be able to do this, or do you want me to get somebody else? All right. You can do it? All right. So we're going to try it. So we're going to let's say medical with a question mark. Okay? All the time you guys have to come up with it.
Sorry to ruin the fun.
No, that's good. So you guys have to come up with the right time. Tell her that to remember 10 people. Right? All right.
Hi everyone, thanks for coming out. I know it's late in the afternoon and you've been doing activities all day. Thanks for joining us. So we have a very special speaker for you. Dr. J. Farrell is a professor here. He is a research professor that does a lot of research on autonomous vehicles. Those are the self-driving, self-flying things that you guys keep hearing about with the drones. So you're in for a very interesting talk. Again, my name is Serena Napan, and
hi, I'm Ali. I'm Professional Development Chair at SWE, the club that organizes this event, Bourns College Day of Engineering. Also, a quick announcement, if there's any Girl Scouts in the room that need a patch, please sure to get that on your way out.
all right, thank you guys for joining us. I'm going to get this started. Can we have a round of applause?
Thank you. All right, everybody. So can everybody hear me? Yeah. All right. So my name is Jay, just like the alphabet. So I don't care if you interrupt me as long as you raise your hand. So if I get too far behind, I'll stop answering questions. But otherwise, interrupt. It's meant to be fun, right? So I don't care if I'm interrupted at all. And we're talking about robotics. Wow, that looks like it's going crazy, doesn't it? All right. And I thought I would start out by talking about what is a robot. So give me a moment here. All right. So what is a robot? That's a kind of neat question because there's so many different things. You know, we picture things like this guy with the looks just like us, but is a computer inside and all kinds of mechanical parts as a robot. But there's lots of other things that could be considered as robots too. And these are things that mechanical engineers, electrical engineers, and computer scientists all collaborate together to build. You know, like I'm an electrical engineer, but I couldn't build this by myself because there's some mechanical parts that have to connect together and move. And then we need to use electricity to both to make the motors move and to send the information around between the different things we're going to talk about today. And then there's these neat things at the bottom: control, sensory feedback, and information processing. And those are the three things I'm really going to talk about today. At the end, I'll come back to a little bit about different types of engineering, but I really wanted to talk about control, sensory feedback, and information processing. And when we think about what is a robot, we all know this robot, right? I almost put R2-D2 up there, but I chose this one instead because he's a little funnier looking. He's not the kind of robot that we usually see, but there's also robots like this. This is a flying robot, right? It's like a little dragonfly, and it's pretty incredible that thing can fly, and it's very tiny. You see it sitting on the person's fingers. In this picture I liked because you can see kind of all the different parts that I mentioned up here. There's some mechanical, right? There's structure there, things that can move, and there's wires in there which are carrying both power to move the thing and information so we can decide what we want it to do. And someplace there's a computer that's doing all the computations to make it happen. As we go through here, there's many other kinds of autonomous vehicles. So it's kind of hard to read up there on the side. This is the Mars lander. And many people might not think of the Mars lander as a robot, but it's at Mars, and it takes a long time when the guys sitting at NASA send information, it's got to get all the way to Mars. So this thing is really flying on its own. It's an autonomous vehicle, and it's got to do all this landing based on sensor information. It measures its height and its tilt and all kinds of other things, and it gets itself to land on a planet that's a long, long ways away. Right? So that's a type of robot. This is a robot. Everybody knows Google, right? Google bought this company, and they want that airplane to fly basically forever over parts of the world that don't have good internet, because then they can deliver internet from these airplanes to those parts of the world. This is from Stanford. This is a vehicle, and mainly I chose this one because look at all these things on top. Those are all sensors. And we as people, we have all kinds of sensors, right? We have our eyes, our ears, taste, feel, all kinds of stuff. But when you design a robot, what engineers do is we design stuff. Hopefully we make life easier and better. But when we design stuff, we have to figure out how do we get this information into the robot, because the robot can't do anything if it doesn't know what's going on around it. And so we put all kinds of sensors on it. And this was part of what's called the DARPA Grand Challenge in 2005, and many teams competed to try winning this challenge. And they all had cars that looked like this. Now we're moving towards autonomous cars where your mom or dad could go out and buy a car that would drive you to soccer or whatever without them being in the car. That's an autonomous car, right? But they'll never succeed if they have that many expensive sensors on it, so you have to do a better job of processing the information. And then these are a couple other interesting robots. This one's called the micro mouse. So students, like we've got some students sitting up here in the front, raise your hands. And I know some of these are IEEE students, and one of the fun IEEE projects is micro mouse. You design this little kind of car, and then other students make a maze, and the robot has to find its way through the maze. Right? It's a fun little project, and if you think about it, it's got a sense. Right? It's got to know where the walls are, not run into the walls and try detecting the open spots, and it's got to remember. Because if I put you in a maze, you might walk for a while and you get over here and you see it goes through, or if you went some other way, it's a dead end. You've got to remember that, or you're going to waste a lot of time doing the same thing, the same dead ends again. So there's got to be some memory map building going on. This is me. I was on a project with the Navy where we put this little vehicle in the water and we wanted to trace plumes. So a plume is like the smoke coming out of a smokestack, and underwater there's these plumes, and the Navy wanted to be able to follow them, and so we built a robot that could follow them. Do you have a question?
You know the Stanford, also my teacher is like for spirit at Stanford, and I didn't know that they can build a Volkswagen.
Yeah, they teamed up with Volkswagen to build that vehicle. It's a really good school, right? There's a lot of really good schools. So this is an example of some people in Italy, and Italy's over here, and China's way over here, and they built an autonomous vehicle and had it drive all the way from Italy through all these different countries, Yugoslavia, I think that's Turkey, Russia, all the way down. This is thousands of miles. And the way that they did it is they actually had a human being drive this first vehicle, and then the other three just followed along, did the same path that it did. This is kind of a follow a leader, but that's an incredible journey. 13,000 miles in 3 months of autonomous driving. And there's some funny videos online because they got stopped by a Russian police officer, right? And there's only a person driving one of the vehicles, right? So, and I'm sure there's a language barrier, so it had to be a pretty funny situation. To make this thing happen, we have to combine together many different technologies. So one is vision. So vision is a camera, and the camera takes a picture, and then there's software that processes that picture, because our eyeballs, we're very good. Like, I can hold up a bottle of water, and you know instantly this is a bottle of water. A computer knows nothing, right? Somebody has to program and say, this is the characteristics of a bottle of water. If you see something with these characteristics, say this is a bottle of water. And the same thing, if we want a vehicle to drive on a road, somebody has to program the computer to understand that the image, some portion of that is a road, and there are edges to the road. And think of all the complexities of things you and I do easily. We walk down a sidewalk. On a computer, somebody's got to program it to recognize a sidewalk, don't go off the edges, all these kinds of things that we take for granted. We can get cars already that do some things autonomously. So for example, cruise control. Cruise control is your parents say, drive 55, the car drives 55. They can parallel park, you can detect vehicles that are in the blind spots, and do other things to avoid crashes. But we're quickly moving towards autonomous vehicles. And autonomous vehicles are going to have many vehicles that can talk to each other and talk to the intersections and decide without the people doing anything what they want to do. And so this is something that's moving forward. And one question is, would you get in the car? Right? Would you get in a car that would drive itself? And this is surveying many different countries. And some people, like Brazil, they're very willing to do that. I think one of the questions here is, would you get in the car? Yeah, so would you ride? And the second is, would you let your kids ride? Right? And they're two interesting questions. And do you know when elevators came out? Elevators, when they first came out in the 1800s, they had a driver. There was a person you'd get in, and you'd say, floor 3, please, and they'd take you to floor 3. And they tried to get rid of the drivers and let the people push their own buttons, and people were afraid. They wouldn't get on an elevator and ride the elevator. And it took 50 years to get past that fear, so like elevators, you know, we could get on and push our own button. And now kids love pushing the buttons, right? They race on the elevator and hit the button. It's a fun part of getting on the elevator. So maybe someday cars will drive themselves. But to make this happen, we have to be able to process information. And so the reason I put these different entities on there is because insects can do things, right? They have these big, long antennas. Those antennas are sensors, and it's sensing what's going on, chemicals that are in the world. And we all see ants and different bugs doing stuff, and they survive, and they do kind of intelligent stuff. Dogs are very smart, right? They've got taste, they've got eyes, ears, whiskers, and they're probably smarter than the cockroach, and we like to think we're smarter than the dog. All of us are doing similar things. There are sensors. Sensors are something that detect, like a thermometer is a sensor. And after it detects, it has to process that, right? We touch the stove is hot. We think very quickly, get your hand off the stove. That information has been sensed that it's hot. Our brain modeled it very quickly, and we reacted. The reaction is a behavior, and the actuator is our muscles, right? Whatever we do in life, we're sensing what's going on in the world, we're processing the information, and then we're actuating. And those same things happen in robots, and we're going to talk about them a little bit. So we like to draw a picture like this, where we have a sensor and it measures something, and we have an action that we want to happen, and so we process the information to see what's actually happening and what we want to happen, give a signal to our muscles, they do something, the physical system moves, right? And this is kind of a picture that we always use, but it's nice to think of an example. So for example, if I point this green dot at the board and I say, keep this in the center of your eye, right? In order to do that, your eye is the sensor, the laser dot is something in the world, and you have a measured action. What is the measured action? As I do this, your eye is trying to keep that in the center, and as I move it, you can either move your eyeball or you can move your head, right? And this is the nervous system sending information to the muscles move your neck and your head, and they cause to do what you want to do, to keep the laser dot at the center of your eyeball, right? And your brain just does all of this processing, and it's very easy because we're humans. We started, do you remember when your little brother, sister, cousin, whatever, when they started walking, right? They would get up and they'd fall over. And it's when we're very young, so we all forget about how hard it was to walk. We can watch them, and when they finally take that first step, we're happy, but then after that, they're running all over. We learn very quickly. But robots don't learn, they have to be programmed to do all this stuff. At least at this point, they don't learn. We program them to do something. So this is a movie that was made by some friends to talk about what is automation.
Automation is the novel name of an ancient wisdom. A wisdom dating back to many millennia, where arts and genius blend together. The science that ensued from it has less than 2 centuries. The name, automation, a few decades. Automation deals with a complex set of activities needed to take rational decisions in a constantly evolving and partially unknown world, relying on available and relevant information. And, of course, is all about mathematics. You start with a formal representation of the system you want to control. You may want to linearize it. You can analyze it by using its phase portrait, by computing the state trajectory, or by looking at its input response. You can switch to the frequency domain by means of Laplace transform, compute the eigenvalues, obtain the transfer function, and plot Nyquist and Bode diagram. Then you can design the control loop choosing a suitable control law amount, state feedback with ball placement, proportional integral and derivative actions on the reference circle, diagonal function or optimal control methods, and don't forget to solve the differential Riccati equation. Wait! Let's keep it simple. Basically, automation gives you the tools to make something accomplish a task automatically. Whatever it is the task you're dealing with, you need 3 fundamental ingredients: the measurement, the control, and the actuation. The measure tells you how things are going. The controller is the brain that, given the measurements, decides which is the action to do. The actuator is the one who executes this action. Let's try to better understand their role with a little experiment. Luigi has a very simple task: brushing his teeth. Let's have a look on what happens when all these 3 ingredients are seamlessly integrated. As you can see, Luigi manages to complete his task without any problem. Bravo, Luigi! Now, let's see what happens if one of these components is absent. Without measurement, without actuation, without control. Okay, Luigi, thank you very much for your help. You can go. And don't forget to pick up your brain on the way out. In this experiment, we have seen the role of each block, and we clearly understand that all of them are crucial to complete the desired task. But how can they interact with each other? How can they talk to each other? What are they made of? How does the controller decide what is the appropriate action to do? Well, automation answers all of these questions and many more. Whether you have to brush your teeth, make a coffee, heat a room, drive a car, control a chemical or nuclear reaction, launch a satellite, efficiently produce and distribute electrical power from renewable sources, or visit another planet, automation is exactly what you are looking for.
Where? Italy, great. How'd you know that? Excellent. Yeah, they're friends of mine from Italy, and they made that video, and they won a contest. There was a contest to make a understandable video about what is automation, and it was a group of 4 or 5 students and a professor, and they made that up, right? So, okay, when we're doing this, why do I have 2 different things on here? I have that there's a real action and a measured action, and the reason that there's You know, the real action is something that physically happens in the world. The car is moving at some speed, and there's some sensor that's measuring how fast it's moving. And the main point is that the measurement and the action are never exactly the same. And to give an example of that, I picked out 3 students at the beginning, and I said, measure this line. All right, there's a line here, and I asked 3 students to measure it, and I got 3 different answers. And this is an example of uncertainty. Whenever we measure anything, there's uncertainty, right? We don't get a perfect answer because there is no perfect measurement. And so then the robot has to decide, based on this uncertain information that it measures, what is it really going to do? And this matters if we're trying to, for example, teach a robot to walk, right? If we're trying to teach a program a robot to walk, it's got to, you know, if it's going to climb those steps, it has to lift its foot a certain height to get to the next step. In the movies that I was playing at the beginning, many of those robots were falling down, right? And it's very hard to deal with uncertainty when you're writing a program and get it to be just right, because if I look at these steps, they're not all the same height, right? And every step in the world is not the same height. If its heel gets stuck, if our heel gets stuck, we fall over, right? So whatever we program, whatever we try to do, has to deal with uncertainty. And one type of uncertainty is random noise. And there's another type of uncertainty. So this next movie, many people might have seen, okay? But do the movie. If you've already seen it, please don't tell who's ever sitting next to you, because part of the fun is trying to do what they tell you to do and seeing what happens. So please don't tell the people next to you what's going on here.
Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes.
How many passes did you count? The correct answer is 15 passes. But did you see the gorilla? This video is from Search by Daniel Simon and Christopher Shabri and is copyrighted.
All right.
It is available for use in talks, training, and teaching on DVDs from VizCog Productions.
All right, so how many people saw it the first time? Very few people, and this is something called selective attention, where when you're focused on something, you might miss other important details or other interesting things. And, you know, think about it. If you're programming a computer to do something and you program it to count the times that it bounces the ball and the gorilla walks through, you might be more concerned about the gorilla walking through than the times the ball's bouncing, right? But when you're programming for something very specific, right? You have something you're trying to do, and you do that, and you might miss other information. And so it's, even though this is, you know, a movie showing even we do this as humans, we're very good at noticing unique things that happen in our everyday life. But when you're programming, it's much harder, but that's another type of uncertainty that we all have to deal with when we're programming things to happen. All right. So the main point is that the real and the sensed information are not always the same. Either something might be missing, or the measurement that I make might be uncertain, but nonetheless, the robot has to keep doing what it's going to do. All right, and so probability can help, and I have some students here. So first, give me a second to try this with one student to do the trick, and then I'll explain how it happens with the 10 of you. So how about you come up and do it with me? I'm forgetting who, oops, where did I put the cards? There we go. All right, so I'm going to do this up here so that everybody can see the cards. And the idea is I'm going to go through, and eventually she's going to have a sequence of cards, and at the end I'm going to say the next card I turn over is the next card in your sequence, and hopefully I'm right. Okay?
Start at 1.
You can pick whatever number you want.
All right.
All right? And you guys out there, you can pick whatever number you want, and you can try along, but it's going to go like this. So like pretend I pick the number 1 and I flip this over, it's an ace. So my new number is 1. Oops, I forgot to turn on the screen. Give me a second here.
Just a second.
Center. It took a second earlier to switch up there. And it went off. There we go. All right. So, for example, if I pick the card 1 and a 6 comes up, now my new card is 6, right? So I'm going to count 6 cards. 1, 2, 3, 4, 5, 6. My new number is a 1, right? And so I count 1, my new number would be 10. And we keep doing this, and eventually I'm going to say the next card is the next card in your sequence, and hopefully I'm right. Right? You got it? Let me shuffle once more. All right, you ready?
Sorry, I lost count.
All right, let's do it again.
I'm sorry.
Okay, and you don't have to do your fingers yet. We'll do that in a
Okay.
minute. If you want to, I don't care. All right? So.
1, 2, 3, 4, 5, 6, 7, 6, 7, 1.
All right, and I think this next one is going to be the next card in your sequence. And am I correct or not?
Yes.
All right. Okay. So I'm not sure. I heard people counting. And did you pick a different number than they were counting or not?
Yes.
Okay, good. All right. So I didn't know what number she had, but I could predict this eventual card in the sequence. So the question should be why, right? And this turns out there's a question mark there on purpose because this isn't magic at all. This is just probability. And to show you that, I trained 10 people, so now you guys come up here. And each person is going to take a different number. So line up, let's put the person with number 1 here. Who's number 1, 2? You guys line yourself up. You're like number 8, right? So you're going to be way over here.
I know, I know.
You're number 9, so go one more person. Which number are you?
I'm 6.
Can you guys all see the screen?
6, 7,
Otherwise,
8,
move back. All right, so get your counts up on your fingers. I'm going to have to come over here. I'm going to shuffle them one more time. All right, so the point here that you're supposed to notice if everybody counts correctly. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, watch their fingers, and over as we go through it, they're all going to come to the same number, right? And the idea is that every time when I pick my number, I've got a 1 in chance I'm counting a number 2. Okay, so I pick a number at random, and it's going to match one of these guys, but it's going to miss the other 9. I've got a 1 in 9 chance of getting the right number. But each time my number comes up and I flip a new card, I've got a 1 in 9 chance. And it turns out that I do it about 7 times as I go through here, and if you take 0.9 to the 7th, it's a really small number. So it's probably the case that at the end they'll all have the same number of fingers up, assuming nobody makes a mistake, right? So let's try hard here. Can everybody see the screen? All right. All right. Who was that? That's you? All right. All right. That's you? All right, good. We're all going. If anybody gets confused, let me know. If you need me to go slower, let me know. All right, so hold your hands up high. Let's see who's where. You're lost?
Yeah.
All right, you guys hold your hands up. All right. All right, we lost a couple, but notice here, I've got, this guy's got 10. These two have, let's do 10s first. Who's got 10? Raise your 10s. Right. So 3 of these have already converged, right? How about 1? Obviously 2, 3 1s, right? You're at 3.
4.
Oh, 4. Okay, and we've got 2 4s. So even though we started out with 10 different numbers, we're down to just 3 different things, right? And if we had had less mistakes, it would have been better. Usually it's about 70%, right? So if I was a wagering guy, it sounds like a pretty good bet to any of these guys at the beginning because I've got a 1 in 10 chance, but at the end I've got a 1 in 3 chance, right? So thank you guys very much. But the idea here is if you understand, yeah, thank you very much. If you understand, so there's always uncertainty in anything we do in robotics, but if you understand probability and statistics, you can make things happen even though there's some randomness involved in making it happen. Let me set this back to what needs to be. All right. Okay, so this is a movie, and we're going to follow this up with another participant. Oops. Let me make this happen. So there's something called a carp pole, or an inverted pendulum. So I brought a lot of markers here. So this is a pendulum, right? If I do this, this is a pendulum, and it swings. And this we say is stable, because even if it gets perturbed, it comes back to where it is, right? Or if I do this, this is unstable. If I let it go, it wants to fall over, right? But you can try balancing that and keep it inverted, right? That's an inverted pendulum. This is a problem we do all the time in robotics because me standing, I'm an inverted pendulum. I want to fall over, right? If my muscles stopped keeping me up, I would just fall over. And many of those robots, they just fell over. I am an inverted pendulum. I'm in an unstable situation, but we're so good at it, we don't even have to think about it. But really, it's this problem. The thing wants to fall over, and we have to work to keep it standing up. And so, who thinks it will be? So I've got a lot of markers here, right? Who thinks it would be easier to balance one marker versus many markers? So who thinks 1 is easier? All right, and who thinks many markers is easier? All right, so we're about 50-50. So let's get 2 people. So I've used all these people up front. All right, come on up. Yeah, you. 1 more volunteer. Who wants to do it? All right, how about you back there? Yeah, come on up. All right. So don't start yet. Okay, we'll wait for, what's your name? Elijah. And what's your name? Wow, both E names. There's not many E names. Is it Elias with an E? Yeah. All right. So do you think it's easier to do long or short? Long. Do you think easier long or short? Long. Oh, you're both, I should have gotten 2 people who are different. All right, so we'll give you the long one. Okay, so you come over here. Don't start yet, all right? You take that one, and each of you try to see how long you can balance that, okay? Oops, takes a little bit of practice. See if you can do it. Oops. And it's much easier if it's longer. And if you understand a little bit of math and physics, you can show why this is true. But if I give you more, it gets much easier. And the reason is because as it gets longer, it has more inertia. Inertia is like mass, it's heavier. And when something's heavier, it's harder for it to change what it's doing. If it's harder for it to change what it's doing, then you've got more time to react. Where when it's really small, this can change what it's doing so quickly that I don't have time to keep it balanced. Whereas I make it longer, it moves more slowly, and we can keep the thing balanced. Right? Have you tried it short yet? Try doing that one. Just take one. Much harder, right? Okay. Now imagine, think about this, you're walking, right? You got to keep yourself balanced, and we do it perfectly, right? All right, thank you guys. All right, so the idea. All right, so me turn this down a little. Of what he's doing here. There's many videos of inverted pendulums online. Let him get a little bit further here. So he shows you the mechanical part. This would be what the mechanical engineer does, right? He figures out the size of the gears and the motors to make this do whatever it needs to do. So there's some mechanical engineering involved. Now he's showing the sensors. And in a moment he'll show the computer. The sensors are sensing. If you want to keep that thing balanced, and when these two people were doing it, they were using their eyes to sense where it is. The Arduino is a type of little computer. And the students at UCR who are doing projects at any university, they're using these little Arduinos. They're really tiny, cheap computers. I don't even know how much they cost, like 10 bucks on that order. But they can do really neat, cool things. They can make great projects. And it's very fun to do the projects. So they have a great time. So this is the type of thing that students would do as a project. All right, so then the question is, how does this really happen in the real world? So does anybody know what SpaceX is? All right, SpaceX, it's, you know, like when I was a kid, it was all NASA. SpaceX is a company that's shooting off rockets. And do you know how the rocket works, what it actually does when it flies? Because we're going to watch it here in a minute. It blasts off like this, and it goes way up into outer space, right? Now it drops off its satellite, and it's flying along like 10,000 miles an hour. First it spins and goes backwards, so it's still flying along, but now it's backwards. But now it fires its rockets to slow down, so now it's just kind of sitting there, and it starts to fall. And as it falls, it's gliding, tumbling, doing whatever, but eventually it comes back like this. Now it's up, or it's right side up again, the same way it was when it launched, and then it comes down and it lands. And it lands on a boat, right? So this is an inverted pendulum problem because that rocket on the bottom is the actuator that's trying to not only slow it down from 11,000 miles an hour, but to land it perfectly on a boat. The first time this ever worked was just this month. So this, I believe, is April 16th.
7, 6, 5, 4, 3, 2, 1.
Notice they're squirting water in at the bottom to keep the stuff cool enough that they don't melt the mechanical structure.
And for deep space exploration tomorrow. Thanks for the
Of it. And I didn't.
Impact chill has begun.
Balance telemetry nominal.
There is a boat down here at the bottom, and look at that, coming down, it's coming down, it's a rocket down, and it lands on the boat.
Landing legs have deployed.
Isn't that incredible?
Seven, 6, 5.
Darn it. All right, I wanted to show you at the end. At the end, did you notice how it was sitting so nicely on the boat? We're all engine nerds, right? We're at this conference yesterday, and we saw that, and we thought that the boat under it was moving, keeping it balanced, because it's got to drive all the way back to the harbor, right? And the SpaceX guy goes, no, it lands. It's so hot that it melts the metal feet of the rocket onto the boat. It welds it, right? So then they can just drive back. It doesn't matter what the sea's saying. So we thought it was a lot harder than it was. All right. So in doing this, so far we've talked about sensing, right? The sensors figure out what's going, or give us information about what's going on in the world. And that's this kind of little piece here. Something processes the sensor. We build a world model. from the world model, then we have to plan. Once we plan, we come up with a sequence of behaviors to do something, and then the actuators make it happen. So far we've been talking about sensors and actuators, and I want to take a minute to kind of make clear what I mean by world modeling and planning, right? So, can you help me? All right. So do you like peanut butter and jelly sandwiches? Tell me how you make a peanut butter and jelly sandwich. Oh, just a second. Let me get this. Can you turn this on? Okay. All right. Do you know how to use that? So tell us how to make a peanut butter and jelly sandwich.
So I put peanut butter. So I put jelly on it first. Then I put peanut butter on it next. I put it on a piece of bread, and then I put another piece of bread on top.
All right. So now let me ask you a couple questions. Where is the bread?
It's in the refrigerator.
All right. And how do you open up the refrigerator? And is it the kind that has the doors like this, or does it have one door and you just open that baby up?
It has 2 doors.
All right. And which shelf would the bread be on?
Like the second shelf.
Okay. So my point here is she's got a model in her head of where everything is, right? And we all do that. So thank you very much. Right? So let's think about it. You come home from school, you're getting out of the car, and plan out, how am I going to get into the house, go to the kitchen, get a snack, and then find some place to study. All of us can close our eyes, and think it through, right? I'm going to get out of the car. I've got to walk some certain set of steps to get to the front door. We know how to open our front door, and we have a picture in our mind of how we're doing all of this. This is a world model. Right? We have a model of how our house is laid out and how we get through our house, and we do it every day when we wake up, right? Brush my teeth, take a shower, find my clothes. We know where all this stuff is, and we make it happen. A robot, either somebody programs that, or it has to build this world model. And in a few moments, I'm going to show you robots succeeding at doing things, and they have sensors. They either have a camera, or they have something like a LIDAR, and I'll explain a LIDAR in one of my slides in a minute. But the reason they're sensing using these expensive sensors is because they have to build a world model so that they can make their plan, right? And to make a peanut butter and jelly sandwich, first they have to get to the kitchen, then they have to face the refrigerator, operate the refrigerator, take out the bread. There's got to be a plan, right? Because if it didn't have a plan, it would take out the bread and then say, oh, I need peanut butter. Go back, and you have to do it. So there has to be a plan in order to succeed in doing something. Then you have to generate behaviors and succeed in each of the behaviors to make it happen. Okay, so at the beginning, there was that sequence of robotic things happening. Did you notice that one of those robots wasn't a robot, it was 2 people? Okay. Those 2 people were making fun of these 2 robots. So this is a company called Boston Dynamics. This is a professor from MIT who left the university and started a company, and he made these 2, they look like dogs, right? But there's many movies online. I'm going to show you one in a moment. I'll show you this one working. But of these things, and they're trying to show you the robustness of the robots. And so the dog will be walking, and they come up and they kick it, right? And the point is, either it will not fall, even though that's a pretty big disturbance, or if it does fall, it will get back up again. They're trying to show that these things can actually work in the real world. And so those 2 people and the one that was shown, they were making fun of it. But I was talking to a guy from Boston Dynamics. They said their company came to a halt that mock YouTube video came out because they all thought it was hilarious, right? Because they're actually doing the video of the big dog with 2 people. But here we're going to see this robot working in the real world. And if you notice, if you look closely here, there's a little cylinder in its head. And all of these have some version of the cylinder in their head. That's a LIDAR. And on the next slide, I'll explain what a LIDAR is. But first, let's watch this. Hopefully the movie happens. Oh, there it goes. All right, and remember, robots don't have feelings because they're going to be picking on this robot, right? But they're trying to show you that it's robust, that it can figure out how to do things. But first, that's very difficult, opening the door. Just a minute with the question. walking on ice. Walking on ice is very difficult for us. And the robot is succeeding here walking on snow. If you listen, you can kind of hear something spinning. That's the LIDAR in the head. It's spinning, and it's measuring where all the trees, the ground, all that kind of stuff are. And then it's solving the inverted pendulum problem. Every time it takes a step, it's balancing on one foot, and it's got to keep that whole robotic body balanced. So, and I believe this is within the last year or so too. So here they're just demonstrating that it can plan a sequence of actions to get the boxes onto the shelf. Here you can clearly see this thing spinning, which is the LIDAR I'll explain next. And if anybody watches Jimmy Kimmel, they have a version of this video with, they voiced over it with the robot talking back, because here they start picking on the robot. And so they're voicing over with the robot being upset. But this is the people who designed the robot basically showing it can replan fast enough to do what it needs to do. Now watch this. This is pretty incredible. All right. So by the way, these are other people's robots. I basically pulled these off YouTube and the internet just to make an interesting talk for people to see. But Boston Dynamics is another company out in Boston. And this LIDAR, this is a sensor that came out of the DARPA Grand Challenge. As far as I know, it didn't exist more than a decade ago. But what it is down in here, there's a laser. Sorry, right here, there's a laser. And it sends out a pulse that hits a mirror, and it flies out, hits an object, reflects back. And so you have the time that it took to travel that distance, and you have the light intensity. Since you have the time of flight and you know the speed of light, you can figure out the distance. But it doesn't send out one pulse. It sends out, so there's 64 lasers set up in a line like this, so it sends out 64 pulses and receives it back, and then it spins. And it spins about 15 revolutions per second, and while it's spinning, it gets 1,000 slices. So this thing is really getting a lot of data, and this is an image of that happening where each one of these lines would be one of the lasers in the 1,000 points. There'd be 1,000 dots coming back, and then there'd be 64 of these different things. And so as you maneuver through the environment, you get these. So this is a vehicle driving through Turner Fairbanks Research Center in Washington, D.C. And is it possible to turn down the lights? There's usually a switch someplace.
How low do you want?
Let's try this one. Presentation. Is that just the presentation lights? That would be just the front. I don't see anything happen. Lecture. Oh, off.
I don't think it's working. I think it's not in sync because the lowest it will go. It's either that or turn them all off.
I don't care. Turn them all off.
But that's all it is.
I don't care. We can turn them back on again, right? Okay. All right, we'll try this one more time. So if we can see it, it's so, you know, the disadvantage of a camera is if I had a camera taking the image and the lights get turned off or it's nighttime, the camera doesn't detect anything. Where a LIDAR, all right, so let's try showing this again. So now as this LIDAR moves through again, oops, darn it. I hit the wrong button. All right, so you can see each of these is the one laser being thrown around. You can see buildings here. You can see some junk piled next to the buildings. You go by this next one, you can see stairs, a little shed next to the building. So the LIDAR is a very popular sensor because I can get that there's something there and exactly how far away from the robot it is. And there's special sensor processing. So thank you with the lights. You're able to extract lots of useful information so you can build a world model and then plan through the world model. And we need that world model because then we build things like this is what's called a high definition map. So if and when autonomous vehicles come, they have many sensors. There's short range sensors, long range sensors. These are LIDAR, camera, radar. These are able to detect all the things that are around the car because when the car is driving, if it's responsible for driving because it's autonomous, there's no person. It has to know the situation around it. It has to know which lane it's in, and it has to know the roads that are coming up. And so one part of this is what's called an enhanced digital map. And like everybody's seen the map on their parent's cell phone or their cell phone. That's a digital map, but it's not very high resolution. It's only accurate to a few meters, and it does not have all the lanes and all the features along with things like stoplights and so forth. And so those things either have to be built into an enhanced map or sensed by the vehicle as it's going around doing its thing. All right, so I'm switching gears a little bit here because some people might not be interested in robotics. I like it. I'm on the information processing side of robotics and trying to figure out where the robot is and the autonomous vehicle is. But there's many other types of engineering. So I've listed a few here. Chemical, so aerospace, biological, biomedical, chemical, so forth. If you have other interests, there's other things you can do, right? Don't look at it and say, oh, I don't care about robotics, I'm not going into engineering. Engineering is a great career. You get to design things. These are new things. They make the world a better place. In the next slide, I'll have many breakthroughs that have made the world a better place. If you like designing things, being creative, making new things, this is just doing it in a technical way, right? You do some math so you figure out how to make it work, and then you build it, and it succeeds. Hopefully you all go to college. College is a lot of fun. It's different than high school or grade school. It's really how much you want to do and how involved you want to be, and I strongly recommend joining a club. There are many clubs, like every single one of these will have its own club. Aerospace will have IAA, biological, biomedical, I don't know. Some of the students might know, but they have their own club. What was it? BMES. So I'm an electrical engineer, so mine is IEEE, Institute for Electrical Electronic Engineers. There's a club for every one of these. Then there's also clubs for certain groups of students, like SWE, Society of Women Engineers. They're the ones putting on this event today, right?
Yeah.
So get involved in a club. You get to make new friends. You get, instead of just sitting in your dorm and watching TV, you're getting to know new friends, having fun, setting up events. So get involved in that. So what do engineers do? So this is from the Atlantic magazine, the top 50 technologies since the wheel. And I tried to color code these a little bit. So like electricity stuff should be there in green. Biological stuff, I believe I put in yellow. I could only go through some. Mechanical stuff is kind of this pink color. This goes all the way back to, thousands of years ago. So the nail was a big invention, right? The nail, it had to be invented by somebody at some time, right? And that's a mechanical device. These are all things that somebody invented, right? And could you imagine your life without some of these things? Could you imagine your life without refrigeration? Somebody had to invent it, and there are still parts of the world that don't have good refrigeration. I believe one of these things on here is sewage processing. Clean water was a major issue all the way until the start of the 19th century. That's only 100 years ago that we discovered germs, and then sewage proper treatment is important. Water treatment. We all need water. Water is going to be a crisis. It takes engineers to build things and make this better. And so another slide saying engineers change the world. This is the last 25 years, so there's many things on here we should all be very familiar with. The internet. Could you imagine life without the internet? Somebody had to invent this, right? Same thing, same count for cell phones, right? Somebody invented the cell phone, somebody invented the smartphone, somebody invented the TV, sorry, my mind works electrically, and this is a slide I use for electrical engineering. But the same thing is going on. The seedless watermelon, somebody invented that, right? Some biological type person said, I can redesign the watermelon so it doesn't have seeds. Personally, I like the seeds in the watermelon, right?
Yeah.
But that's the job of an engineer, to use science and math to make the world a simpler, better place in some sense. So, you know, you're here. I assume you have an interest in math and science. Work hard, develop good study habits. Take all the math and science you can. Math and science will pay off in whatever career you decide to do. And when you do that, ask questions. All right? The main one at the bottom here is you're here because you or your family thought it would be interesting, right? And your family is going to support you throughout. When a university accepts you, they're accepting you because they think you can succeed, right? If they didn't think you would succeed, they wouldn't bring you there. But in the end, it's got to be the student who makes it all happen. So study hard, take math and science, and enjoy it. So thank you very much.
Thank you. We'd like to thank Dr. Farrell by giving him the SWE gear.
All right.
Hopefully you rock this t-shirt next year when you come too.
All right.
Thank you. And we are raffling off this t-shirt, so hang tight. We're going to call some names. We took all of your names down. Did anyone not get to sign? Okay, you'll be number 60. 60. So we're going to do a random number generation. We have a couple of shirts to give out. If we call out your names, just come down, please.
Hold something.
Yeah. Thank you. All right, t-shirt? No, just keep going.
Okay. So first number is number 15.
Which is?
So that is
15.
Angelica Rosales.
All right.
Okay. Next one is number 3, Patricia Heisel. All right, number 19.
Actually, five.
What?
We have 5.
Kennedy C.L.
All right.
All right, number 47.
This is the smallest. You can tie it.
Adam Drake-Walter. And then number 31, Andrew Ventino.
Thanks you guys for coming out. There's still some activities and still the food trucks if you guys are still hungry. And let us know if you have any more questions about science